today we're going to start with linear programming. I think it's a very fun topic because it's very visual. Okay, and that's how I want to do it. I don't want to get into algebra and formalization and so on. I want to give intuition based on geometry of the problem. Okay, so how many of you know polygons? We all know polygons, right? Do we know polytopes? Okay, three-dimensional polygons are polytopes. Okay, so in some sense, this room is a polytope if there are not these extra columns and if that side is completely closed properly and so on. Another example is this is a polytope. Okay, its surfaces are straight. Okay, and it's convex. Okay, so if you take the extreme points of this object and take all the convex combination, that will form the polytope. Okay, and have you seen so you might have seen polytopes everywhere, right? Generally, rooms are square and there are not these curves and so on, and that forms a polytope, right? What about for polytopes in 4 dimension? Can we imagine that? Yeah, wise people say that trying to imagine beyond 3 dimension could be fatal. Okay, so let's not try and imagine beyond 3 dimension. We'll keep all our imaginations up to 3 dimension, but everything works for general d dimensions. Okay, any d for any integer d. Okay, so let's start with why linear programming. So let me tell you, I have a factory. Yeah, apart from teaching, I do this also. So I have a factory and that produces 2 goods, 1 and 2, and it uses A, B, and C, these 3 goods. Okay, now the way the production goes is that to produce 1 unit of good 1, I need 1 unit of good A and C both. To produce 1 unit of good 2, I need 1 unit of B and C. Now suppose I have 200 units of A, 300 units of B, and 400 units of C. Now the question I have is, I want to maximize my revenue. Okay, if I sell good 1 unit of good 1, it gives me $1. Okay, and good 2, a unit of good 2 give me $6. Okay, how many units of product 1 should I produce, and how many units of product 2 should I produce? Simple question. Yeah.
300 units of product 2 and 100 of product 1.
Awesome. Okay, so he's saying 300 units of product 2 and 100 units of product 1. Why? Why is that the best?
Because you can either maximize the number of product 2s or you can maximize the number of product 1s. Since product 2s are worth more, you can make more on that maximum.
Okay. Yeah, so he's saying that because product 2 is giving me more profit or revenue, so I should try to maximize product 2, and then if I cannot produce product 2 anymore, then I can try and produce product 1. Right? Now, this is a very simple scenario, right? So we can formulate it as a linear program to argue it. If you want to argue it very formally that this is the best you can do, so this is our problem. Let's say I produce x1 units of product 1 and x2 units of product 2. So my profit will be x1 plus 6x2, right? Because the price of good 1 is 1 and price of good 2 is 6. Fine? Then I know that I have exactly 200 units of A, but A is used by only 1, product 1, right? So x1 cannot be more than 200. The number of units I can produce of product 1 cannot be more than 200 because it uses A, and I have only 200 copies of A. Right? Similarly, x2 cannot be more than 300 because 2 uses B and I have at most 300 copies of B. Right? So these two are natural upper bound on the quantities of product 1 and product 2. C is used by both, but I have 400 units of C. So it says that x1 plus x2 cannot be more than 400. And of course, I'm not going to produce negative quantities. Right? So these constraints, these three constraints can be modeled as these three linear constraints. And then maximizing the revenue is just this, maximizing this quantity. Now it's relatively easy to see why that is the right answer, right? Because x2, I cannot produce more than 300. And I want to produce it as much as possible because it has a coefficient of 6. So when I set x2 to 300, I can set x1 to at most 100, and that's it. Okay, so this is a very simple, I have a very simple factory, I don't produce too many things. But suppose I had like thousands of things produced, right? And using thousands of raw material. Then the answer won't be so simple, right? And linear programming was exactly kind of invented in 1920s, 30s for this kind of questions. People came across this kind of questions and they said, oh, how do we do this? Right? When there are too many constraints, too many variables to play with. How do you optimize? And how can you make sure that whatever you are doing or whatever solution you are giving is the best solution? And that's where stemmed the theory of linear programming. And it's really beautiful, okay? It's heavily used not only for solving such problems, but even more complicated problems where you don't see any direct connection of linear programming. Okay, it's a beautiful theory and also very, very powerful tool. So all in all, we can write our problem as a linear program. What do we mean by a linear program? The constraints are linear inequalities, and also the objective function that you want to optimize, maximize, or minimize, whatever, is also linear of the variables that you have defined. Okay. Okay. Now suppose we have been learning about MaxFlow, right? All the algorithms, everything, right? This problem can be stated as a linear program. So suppose I have this ST network, directed graph. It's a DAG. Yeah, it's a DAG. Now I want to find how much maximum flow can I send from S to T. So what I'm going to do is, I'm going to define a variable for a flow for each edge. Okay? So let's say fs3 will be how much flow goes from S to 3. That is my variable. Okay? Similarly for each edge. Okay? So these are my variables, fs1, fs2, fs3, fs3, 2, 5, 1, 4, and 4, 2, and for each edge actually, 3, 5, 6, 5, 5, 4, 4t, 5t, 6t, all of them. Okay? Now, what is the obvious constraint you have to have? The capacity constraint of the edges. Right? So the flow cannot be more than the capacity of the edge. So these numbers on the edges are the capacity of the edges. So these constraints are saying that the flow on S1 edge cannot be more than 15. Flow on S2 edge cannot be more than 5. On S3 edge it cannot be more than 10, and so on. What other constraints do we need? Can there be negative flows? No. So the flows have to be positive. So greater than or equals 0. What else? The crucial constraint of a flow. Yeah. Mm-hmm.
All the flows going into a vertex have to be the same as all the flows coming out.
That's the property of the flow, right? The amount of flow that goes inside a vertex should be exactly equals the amount of flow that goes outside the vertex. So what can I say about vertex 1? What is that constraint? How much amount of flow is going inside vertex 1? Fs1 plus F21, right? And how much can go out? F14, right? So that's the constraint we get for 1. Fs1 plus Fs2 should be F14. What will be for 2? S2 plus 3,2 plus 4,2, right? All incoming edges should be equals 2,5, only one outgoing edge. Or is there a, yeah, sorry, 2,5 plus 2,1, two outgoing edges. Okay, so these are just flow conservation constraints. And they are linear. Right? So all the flow conservation constraints can be written as these equalities. Incoming flow, so look at all the incoming edges. Add up those variables. Equals, look at all the outgoing edges, add up those variables, and they should be kind of, yeah, they should be equal. Right? And what do you want to maximize? Exactly. So in words, you want to maximize the total flow going out of S. Right? Because you know that because of these constraints, the flow will be conserved at every intermediate vertex, and exactly that amount of flow will reach T because of these constraints. So non-negativity, and then you want to maximize the total flow going out of S. So S1, S2, S3. Do I have to write conservation, flow conservation for S and T? No, right? Because we don't have to conserve flow at S and T, because S is the source and T is the destination. The flow goes out of S and comes into the T. And for this, the graph need not be DAG. Okay? So this example is, it's a DAG. But even if there are cycles, you can still write this linear program. Okay, and show that this, if you solve this linear program, you will get the maximum flow. Now, for this LP, is it, I mean, it's not obvious anyway, but it's not even kind of clear how to find the solution immediately. I mean, we know these max flow algorithms, Ford-Fulkerson and all, right? So we know how to solve max flow problem. But if I just tell you this LP, it's not clear how to optimize this. So in general, suppose you have a general graph, then, and the edge E has capacity CE, and let's say we define a variable FE for the flow on edge E. Then we want to maximize the flow going out of S, so you sum up all the edges which are going out of S. For that, you sum up their variables. And you put a capacity constraint, so the flow cannot be more than its capacity for the edge. These are the flow conservation for all the nodes which are not S and T, and the non-negativity constraint. So if there are n nodes and m edges in the graph, how many variables do I have in the problem? N nodes, m edges. What are variables? Edges, right? We have one variable per edge, because every variable defines a flow on some edge, right? So we have m variables. And how many constraints, linear constraints, do we have? So m of these plus m of these, right? And how many of these flow conservation? N minus 2, right? For all node except for S and T. Okay, so we have m variables and the constraints are m plus n minus 2 plus m. Okay. So, yeah, it is powerful enough to solve this problem actually. And I don't know if you have seen min-cost flow. Did Chandra cover min-cost flow? He did, right? So what is min-cost flow? You want to send some minimum amount of flow from S to T, but there are cost, in addition to the capacity on the edges, you have cost on the edges. Imagine a kind of a traffic network, right? As more and more traffic goes through a road, the congestion may increase and the delay time may increase, right? So you want to, so WE is the cost of unit amount of flow on edge E. Then you want to minimize the total cost of the flow. The total flow going out of S should be at least V. Here we have upper and lower bound on the flow, on the edges, and the flow conservation. So you could also sometimes say that I need at least this much flow on this edge. So you could also put a lower bound here. Okay, these are all variants of the flow problem. Okay, you could also have something produced at nodes, intermediate nodes. Okay, so say at node 1, I am capable of producing flow of 1 unit. Then how should this flow conservation change? So whatever flow comes in should go out, of course, but I am producing extra flow at node 1. So that extra flow should also go out. Okay? So outgoing should be incoming plus 1. So here you will have a minus 1 here. So I'm just trying to say that this tool captures almost all variants of flow problem. Okay, even if you make it more and more complicated. Okay, now the number of constraints have increased because you have these upper bound constraint which is extra, and this requirement that the flow goes out of S is at least V. So you have plus M and plus 1 here. Anyway, so in general, a linear program is defined by a linear objective function which you either want to maximize or minimize, doesn't matter what, and linear set of constraints, equality, inequality, whatever. Here xj's are variables and the rest are all constants. So Cj is a constant, Aij's are constant, and Bi's are constant. Okay? And we can think of this problem in a matrix form where the Aij coordinates can form a matrix. So if there are, say, total n constraints, and suppose there are d variables, then A is n cross d matrix. You see that? Because every row of A will correspond to some constraint here. Okay? And every column corresponds to a variable. And B is a vector and C is also a vector. B is n-dimensional vector and D is a d-dimensional vector. Now, there are many ways to, many canonical form of linear programs, and we will use this one. Is this general enough? Can I convert this linear program? So here you have less than equals, equals, greater than equals, but I want to allow only less than or equals. Can I change the previous linear program to get only less than or equals in the linear constraints? So suppose I want to get rid of this equality and just represent this constraint as some set of constraints which are just saying less than or equals. Yeah.
You just do less than or equals and then greater than or equals for that constraint.
But I don't want to allow greater. Okay, you're right. That's great. So that's one step. And now if I don't want to allow greater than or equals, then? So if I have an inequality, A less than or equals B, what can I say about minus A and minus B? Exactly. So minus A, if A is less than or equals B, then minus A will be greater than or equals minus B, right? So if you multiply the constraint by minus 1, so if I multiply this constraint by minus 1, so make this minus Aij and this minus B, then it will be less than or equals. Right? So given any linear program, you can convert it to a canonical form. Okay, so it is without loss of generality to consider only this type of linear program where you have just less than or equals. Okay, so if you have equality, you can represent it as less than or equals bi, and then say minus, and then again less than or equals minus bi. Okay. And again, if you have greater than or equals, just say minus of that is less than or equals. Do we agree on this? Questions? Okay, we don't have to finish everything, but I want to make sure that this is clear. The formation of the linear program is clear. What are the coefficients? What are the variables? Why we call it a linear program? Okay, this is the basics. If this is not clear, everything will be blank from here on. So ask questions if something is not clear. Just so that it's easy to explain, you will see, I mean. I want to kind of, so we want to design algorithms to solve this problem, right? If there are greater than or equals, less than or equals, equality, it's difficult to keep track of each type of constraint. So just convert it to one form and then to argue about it. Good point. Okay, great. So he's asking, suppose I don't want to say less than or equals, I want to say just less than. The problem is here, that makes problem harder, okay? A bit harder, because that says that the set of feasible solutions, so let's say forget about the objective function. Look at all x that satisfy this constraint. Okay? I claim that it is a closed set. What do I mean by closed set? If you take a sequence of points inside this feasible region, and if it has a limit, then the limit is also in the feasible region. You know the definition of closed set, right? As soon as you make it strictly less than, it becomes an open set. So suppose, imagine the constraint. Oops. Okay. So suppose you have x1 less than or equals 1 and greater than or equals 0, right? Or you have x1 less than 1. Okay? And suppose I have these two possibilities and I want to maximize x1. What is the solution for the first one? Only two constraints. x1 has to be between 0 and 1 and maximize x1. What is the solution for first one? when I say less than or equals? 1, right? What is the solution for the second one? We don't have an answer. Whatever solution, you cannot give me 1 because 1 is not feasible, right? Whatever you give me, you will give me some number which is less than 1. I can produce a number bigger than that, which is not 1, and that will be better. So this is an issue. There may not be a solution to that problem. I mean, yeah, basically. Yeah.
Could you state what A, Ij, and Cj would be in terms of that original factory problem? Because I'm having trouble understanding kind of what those coefficients represent.
Okay, let's go back then. Okay, good. So what is C? Tell me. Let's change the color. Okay, what? So the canonical form is maximize Cj xj such that summation of Aij for all I xj is less than or equals Bi. Okay, so now what is C1? 1, right? C2, 6. Okay, 3 constraints. So here I was going from 1 through n. So n is 3 for us. So what is A11? What is A12? 0, right? Is that true? Is that clear? No? So this constraint can be written as, so we have only 2 variables, right? Suppose I write this constraint when I equals 1. Then it is A11 x1 plus A12 x2 is less than or equals B1. So if you look at this first constraint, there is no x2 here, right? So this coefficient is 0. There is x1 and the coefficient of that is 1, so this is 1. And what is B? B1. 200, right? This is B. Okay, thank you for asking. Was for the second one. So, okay. Now what is A21? So A2, so this is the second constraint. So A21, that is in the second constraint, what is the coefficient of x1? 0, right? In the second constraint, what is the coefficient of x2? Right? So A22 is 1, right? And what is B2? What is the right hand side of the second constraint? So B2 is 300. Okay? B1 is 200. And what is A31? It's 1. A32 is 1. And B3 is 400. Right? So if I want to write this in the matrix form, how can I write that? So I can say maximize 1, 6 dot product with x1, x2, right? Such that, I don't have space here, so I'm writing here, 1, 0, 0, 1, 1, 1, x1, x2 is less than or equals 200, 300, 400. And of course, you have these two constraints in addition that you have to add here at the end. Yeah.
So if I understand this correctly, the two other constraints are greater than, so you're going to have to do
Minus. Yes, yes. Yeah, so this, if I want to say x1 greater than or equals 0, I have to say x minus x1 less than or equals 0. And then this is the fourth constraint, so I'll have A41 to be 1 or minus 1? Minus 1? Minus 1, right? Because the coefficient is minus 1 here when I say less than or equals. Right? And A42 will be 0 and B4 will be 0. So here there will be another minus 1, 0, and here it will be 0. And there will be one more actually for x2, which will be 0, minus 1, and here it will be 0. Sorry for the tiny handwriting. But the point is clear? Not clear? Good. Okay. Yep.
I thought there's another constraint for less than or equals 5.
Yeah. So for,
With minus.
so did I miss anything? So you're saying this one?
No, for when you go back to the conversion slide, the conversion slide. Yeah, there's a minus sum of Aij, Sj, less than,
This one?
yeah,
This one?
for the first one.
But I don't have any equality in that program.
Oh,
Do I have equalities in that program? No equalities. So I don't need to do that. But I need to take care of these greater than or equals, because this is not in the R form. So when x1 is greater than or equals 0, minus x1 is less than or equals 0, right? So it's the same thing. Just say minus x1 less than or equals 0. And then that constraint, in that constraint, the coefficient of x1 is minus 1, for x2 is 0, and b4, the right hand side is 0. Right? Okay. Okay. Okay, so we are all good with the canonical form, right? Okay. Okay, so we will generally think about represent it, because we don't want to write ij again and again. We'll just represent it in a matrix form. So we have n constraints, d variable. So matrix A is n by d, that are these coefficients of in the linear constraints. B is the right hand side, and one coordinate for every constraint, and there are n coordinates, n constraints, so it has n coordinates. And C is the cost vector or objective value, whatever you want to call it, objective vector, which you want to maximize C dot x. Okay, suppose I want to minimize C dot x. How do I convert it to maximization? I missed that point. Suppose in the original problem, like the min cost flow, that was minimization, right? Remember? This is minimization. So we now know how to convert this to less than or equals. We know how to convert this into less than or equals, right? But we haven't talked about how do you convert minimization to maximization. minus, right? You just multiply this entire thing, this cost vector, by minus. So if you are trying to maximize some quantity, some number, you just minimize the minus of that number. Right? So that's how you can convert maximization to minimization. Okay, there are other standard forms people study. Okay, if you see other notebooks and notes, people might be talking about this kind of form where you have less than or equals constraint and non-negativity on the variables separately. Okay, you may have minimization with the same type of constraint, or you may have, say, minimization with equality constraint. All of them can be made a standard form. Any of them can be converted to any other by adding extra variables or extra constraint, and still the size of the problem will remain polynomial. What do I mean by the size of the problem? How many bits do you need to represent this A, B, and C? Okay. So you can try and think about this. How do you convert from, so you have seen 4 forms. How do you convert from one to another? You can try and think about it. Especially, how do you convert an inequality to an equality? Okay, it'll be fun. Just think about it. Okay, so it's a long history, as I was saying. It was first studied by Kantorovich in 1930s. He's a Russian. And basically to solve some economic problems, some factory problems. Okay, maybe much more complicated, but some kind of economics problem. Okay, but we didn't know about it for a long time, for 10 years actually, almost. Then it was reinvented by Kopman in 1940s, again for economics applications. Okay, you have some set of constraints, you have some resources, you want to use them and maximize your profit or whatever throughput. How do you do it? Okay. The first algorithm came in 1947 by Danzig. It's a beautiful algorithm we'll see today. Okay. And both of these guys got a Nobel Prize, but Danzig was ignored. Because these guys are economists and Danzig is a mathematician, actually. And they thought that, sadly they thought that, actually they did protest, that Danzig should get this prize also, because Simplex is a very powerful algorithm, in the sense that if you see the algorithm, you will see, oh, what is there? It's so simple, okay? But it is so fast, even today, even though we have so many polynomial time algorithms and blah, 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 people still use Simplex in practice, just because it is fast. Okay. Anyway, so much so for Nobel Prize. Okay, let's get back to this factory problem and let's see how should we solve this in a systematic way, in a way in which we can solve any linear program. Okay, so for that we need to understand how these feasible points look like, so that we will know where this quantity will be maximized. All the x1, x2 which satisfy these linear constraint, okay, let's call them feasible points. And subject to those feasible points, we want to maximize this linear quantity on x1, x2. Okay, okay, so let's draw it. It's finally 2-dimension, so not too bad, right? And linear constraints. So what are linear constraints? They are just lines in 2-dimension. Right? So the first constraint is x1 less than or equals 0. So this is, say, the x1 equals 200 point. And this constraint is just saying that if you draw this line, vertical line, all the points on the left side of this do satisfy this constraint. Right? x1 at least 0. So x1 cannot be less than 0. So all the point on the right side of the x2 axis are feasible. Similarly, x2 cannot be more than 300, so below this line. And x2 has to be at least 0, so above this line. Okay? And the third constraint, which is more interesting, is saying x1 plus x2 should be at most 400. So when, say, what is the intersection of this? So this is the line. It intersects x1 equals 200 and x2 equals 300. So this is x1 equals 200 line. So if I set x1 equals 200, x2 can be at most 200, right? So this will be a 200 point. And all the points below it are feasible points. So this polygon that we got is the set of feasible points. I'm just putting what do we mean by this constraint in this geometric view. Okay. So these are all the feasible values of x1 and x2. And the objective function is, so this line represents all the points where the objective value is the same. Okay? So its normal vector will be 1 and 6. If you look at the normal vector to this red line, that's 1, 6. Okay? So if you look at all the points where, say, x1 plus 6x2 is, say, whatever, 1, that will form a line, right? So all the points which intersects this red line with this shaded region are the points where x1 plus 6x2 has the same value. Now you want to find a point in this black shaded region where this value is maximized. So as you kind of change x1 plus 6x2 equals whatever, it moves up, right? Because those are parallel lines. Right? And the point where this line leaves the polytope is the optimal point. So first thing we saw is that we can represent these constraints in 2 dimensions through lines, right? So if I just look at x1 equals 200, that is this line, the vertical line, right? If I look at x2 equals 300, that's the horizontal line, right? x1 equals 0 is this x2 axis, because on x2, x1 is 0 on this axis, right? x2 equals 0 is this x1 axis, right? And x1 plus x2 equals 400 is this line. And then you see which side of the region you want. And on top of that, you want to maximize this. So what you do is, say you put some value for x1 plus 6x2 equals something, say 1. And that will be a line which may intersect this shaded region. And then keep increasing the right-hand side for that. And you will see that it will, so if you have, say, x1 plus 6x2 equals 100, or x1 plus 6x2 equals 400, what can I say about these 2 lines? These will form 2 lines here, actually, like that. Right? What can I say about them? They are parallel because their coefficients are same. Okay, so these are parallel lines, and you keep increasing their right-hand side. Okay, so say 400, then 500, and at some point it will escape the polytope. And that will be the maximum point. And in this case, it will be like 1900 here. So when I say this is equals 1900, that is the point where it will almost just touches the polytope. 1900 plus epsilon, it is out of the polytope, no intersection. Okay. So each constraint is a half space. Okay. So when you say x1 less than or equals 200, that line, x1 equals 200 is this line, and all the region on the left-hand side of that is feasible for that constraint. So that's called a half space or half plane, because half of the plane is infeasible, other half is feasible. Feasible region, intersection of feasible region formed a polygon, right? This is a polygon, the shaded region, right? For a fixed value of objective function, we get a line, and parallel lines correspond to different values of the objective function. And optimum is achieved when the line leaves the feasible region. Now, if we go to 3 dimension, each constraint will define a plane now. Okay? So like in this, if I think of this as a polygon or a feasible region, suppose there is this here x-axis, y-axis, z-axis, and this is just saying that x is at least 0, at most 1. Okay? Similarly, y is at least 0, at most 1, and z is at least 0, at most 1. Okay? So this plane is z equals 1 plane. This plane is x equals 1 plane. And so on. Right? So every inequality will define a plane. Okay? And when you say less than or equals, it will define a half space of that. So everything kind of generalizes to 3 dimension. So here you have this polytope, and these are the faces which are defined by these constraints, 1, 2, 3, 4, 5, 6. Those are the numbers you see here. This is 4 here, and so on. x1, 1, 1. Where is 1? Here. x1 at most 200. So this is a 200 point here. Is this geometrical view clear? Somewhat? Right? When you say x1 equals 200, are you putting any restriction on y and z? Any point where yz be anything, but x1 equals 200 will be on this plane. Right? So that's why it is this plane, where it cuts x1 only at 200 and does not cut y at x2 and x3 axis. Okay. So now if you put these bunch of planes around, and then say that only one side of this plane is feasible, then that will form a polygon. Another point is that you can actually transform the problem where you are just maximizing some coordinate, some variable. That's it. So suppose we have this problem. Let me call this x1 plus 6 x2 as z1. And let's say z2 is just x2. Then x1, so z2 is x2, and this quantity is z1. So I can write x1 as z1 minus 6z2, right? I can replace here z2 and then say x1 is z1 minus 6z2. And accordingly, replace everywhere x1 equals z1 minus 6z2 and x2 equals z2. Okay, in all the constraints. We'll get a new LP, and these two are the same LPs. Okay, but the funny thing is here we are just maximizing one coordinate. Okay, good. Now suppose you have a polygon, okay, and you want to maximize, say, just x1 or z1, whatever variable you want to give in that polygon. Can it be an interior point of the polygon? So one interpretation of polygon we see was like you put these lines, you see which side of the line is feasible, and that forms a polygon. What is another interpretation of the polygon? So if we see the extreme points, the vertices of the polygon, here if I see these, say, all these vertices, this, and this. What can I say about this gray area in terms of these vertices? Yeah.
You could define the edges as a set of points. Is that what you're trying to do? Each edge or each surface based on the polygon is a set of different coordinate points.
That is true, but what can I say about any point, say, on this edge in terms of the corner points on this edge? So there is this corner point and this corner point, right? Right? What can I say about this point? Can I write this point in terms of these two corner points, say A and B? It's a convex combination of AB, right? What is convex combination? Okay, so convex combination is, so let's say this is what point? This is 0, 300. And this point is, so you have x2 equals 300, so x1 is 100. So 100, 300. And this middle point is, say, 50, 300. The y coordinate has to be 300, right? Because it is on x2 equals 300 line, right? So I can write, say, this is a C point. Then I can write C equals half A plus half B. See? That's a convex combination. Convex combination is a linear combination of the given points where the coefficients are non-negative and they sum up to 1. You might have seen this, right? Somewhere? No? So any point in the shaded region is actually convex combination of its extreme points. And yeah, I mean, that kind of tells you that if some value is, okay, another point. If I have, say, two numbers, say 100 and 200, and I take a convex combination, lambda plus 1 minus lambda, and lambda is between, say, 0 and 1. What can I say? What is the upper bound and lower bound on this point, say, tau? What are the upper bound and lower bound on tau? Yeah. So upper bound is, yes, 200, right? And it is achieved when you set lambda to 0, right? But yeah, so the lower bound, when we set lambda to 1, what will we get? Lambda equals 1. Sorry, it's 100. Sorry. Oh, no. Okay. Yeah. 100, 100, 100. So 100, right? So the point I'm trying to say is that if you take convex combination of a set of numbers, then the maximum and minimum number that you can produce through any convex combination cannot be more than the maximum number in the set and minimum number in the set. Yeah.
How can we guarantee that our linear programming is going to give us a shape which is convex, which doesn't really contradict?
Good point. You can prove it. I mean, I'm trying to give you, so if you look at the canonical form, okay? Now let's say x1 and x2. So what do I mean by, what do you mean by convexity anyway? One definition of convexity is if 2 points are feasible, then the line joining them is feasible. That's the definition of convexity. Agreed? So now I'm saying that x1, x2 are feasible. That means ax1 is at most b, right? And ax2 is at most b. We know this, right? This is given. Now suppose I say, take a convex combination of x1 and x2. So I say x equals, say, lambda x1 plus 1 minus lambda x2. What can I say about ax? What is that? For lambda between, sorry. What can I say about ax?
So it's down to the values AX1 and AX2.
Yeah. So by linearity, because this is a dot product here with matrix, right, of the vector. So I can write just this as a, so let me just replace x, right? So lambda x1 plus 1 minus lambda x2, that's my x. And by linearity, I can write this as a lambda ax1 plus 1 minus lambda ax2. What is an upper bound on ax1? So here it is important that lambda and 1 minus lambda both are positive values, right? So if I multiply this by lambda and this by 1 minus lambda, right, I get that this is at most lambda b plus 1 minus lambda b. So here b is a vector, which is exactly b lambda plus 1 minus lambda, which is b. So if you take 2 points which are feasible, which satisfy this linear constraint, then any convex combination will satisfy the linear constraints. And that is why the feasible points is a convex set. Okay. So, yeah, we were here. So if you just want to maximize this one coordinate, it cannot be in the interior, right? Because interior point is convex combination of extreme points. And the convex combination cannot have a coordinate which is larger than its extreme points of which you took the convex combination, right? So the optimum has to be at some extreme point of the polytope, which is typically will be a vertex. It could be an edge. If this was a vertical line, it will be like entire edge is optimum, but there will be always a vertex which is optimum. Now if I tell you that there is always a vertex which is optimum, can you give me some naive foolish algorithm? Yeah. Best one, right? Check all the vertices and see which one is the best one, where the objective value is maximum, right? How do vertices are formed? So how do I compute the vertices? So in this, these are vertices, right? This is a vertex, this is a vertex, this is a vertex. How is this formed? Intersection of two lines form a vertex, right? And every vertex is feasible, like any intersection is feasible? See, this is not feasible, right? These are formed by the two lines, legitimate lines, but that point is outside the feasible region, right? So how many, at most, how many vertices will there be if there are n constraints? Sorry, yeah? N plus 1? So you are really near, but so that any two will intersect, and choose 2, right? Because any two, if I draw 2 lines, right? If I draw a lot of lines, at most I am saying, at most how many intersections can there be? You are right, it is kind of n plus 1 in some sense. Okay, you are optimizing, right? Because for every hyperplane there can be at most 2 vertices on the hyperplane. So on any line that there can be at most 2 vertices which are feasible. So per line 2 vertices, so at most order n vertices in some sense. But when you are doing naive search, when you don't know which vertices are feasible and which are not feasible, you'll have to check every possible intersection which are n choose 2. And so total n, order n square. For every vertex you can check whether it's feasible and then what is the objective value. And among all the feasible ones, pick the one which has the maximum objective value. Right? Okay, so order n cube time algorithm, because to checking the feasibility of a vertex may take order n time, right? Because for every constraint you have to check whether the vertex satisfies the constraint or not, and there are n constraints. What if we are in D dimension? In D dimension, a vertex is formed by intersection of D hyperplanes, D inequalities. Okay? So how many possible intersections if there are n constraints? If you pick any D of them which are linearly independent, that will form a vertex. Feasible, infeasible, we don't know, but that will form a vertex. N to the D. Why n to the D? Basically n choose D, right? And for every vertex, again, you can check whether it's feasible, infeasible, and check the optimal value, and then pick the one with the maximum objective. Is this a good algorithm? Too much, right? Even if you want to solve the flow, there were like m variables. N to the m algorithm. Too bad. Right? Just go back to the normal flow algorithms. Okay, so can we do something, and how do we kind of compute a vertex given the D hyperplanes? It's just Gaussian elimination. So basically you want to solve this system Ax equals B where A is not the same A, you just took the D rows. Every row represents a constraint, right? So take D of them, and similarly the same BIs, and then you solve Ax equals B, and this is just, you just have to compute A inverse and multiply it with B, and that will give you the vertex. because it's intersection of D hyperplanes. What are hyperplanes? Hyperplanes are inequalities, those linear constraints. So hyperplanes are formed, a hyperplane is formed by where that inequality is equality, right? So in this 3-dimension, x1 equals 200 forms this hyperplane 1, which is cut by this hyperplane 3. And when it is cut by this another hyperplane 7, which is x3 at least 0, it forms this vertex C. So in 3-dimension, when 3 hyperplanes meet, they form a vertex. When 2 of them meet, what does it form? A line, right? When 1 and 3 meet, they form this line. Look at this room. It is a polytope in some sense, if we forget about these extra columns and these glitches. If you look at the ceiling, that's a plane, that's a hyperplane. And look at this wall. That is also a hyperplane. And when they meet each other, when they cut each other, that forms this line, right? And when you go straight on that line, suppose this was like complete wall, when it hits this hyperplane, that will form a vertex there. Now you will try to see polytopes everywhere. Actually, you will see it everywhere. Okay, good. So far what we have seen is that we have the linear constraint which define the half spaces and equalities which define the hyperplanes. When you take the intersection of these half spaces, because these inequalities, that will form a polyhedron or polygon. Polyhedron is the one which is unbounded. So imagine this room which has no end in the back. These lines just go back up to infinity. There is no wall in the back. That will be a polyhedron. And we kind of, because it's a linear optimization, we are optimizing a linear function over a convex set. It has the local optima are global optima. Okay, you can try and argue about this, why this is true. And that is why the optimal value is attained at a vertex. We kind of argued why optimal value is at a vertex, right? Basically, every interior point is a convex combination of extreme points. So if something is, any linear function has to have a better value at the one of the vertex than at the interior point. Okay. And that linear function we took as single coordinate, but that is true for any linear function. Okay. So I don't think I should start simplex, but it is basically just vertex hopping algorithm. You move from vertex to vertex, and eventually you know you will reach an optimum vertex. Okay, so you start from vertex, some vertex, any arbitrary vertex, go to a neighbor. If it is not optimum, then you go to its neighbor, and so on. The questions are which neighbor to go to, right? And when to stop. How do we know that the current vertex is the optimum vertex? And how much time would it take? Why people are still using it? I mean, this is like 60, 70 years old algorithm. Okay, so let's do it next time. But it will be good to understand this polyhedral geometry. Okay, what are hyperplanes? What are half spaces? Okay, what do I mean by intersection of hyperplanes? Okay, what do they form? Okay, some intuition about that would be helpful for the algorithm. And also about this local optimum is global optimum. Okay, try and think about it. If it is not clear, I'll explain it in the next lecture. Okay? Okay.
I understand if there are any constraints and like for 2D space there should be n choose 2 different combinations and n choose 2 vertices. But you say for each vertex you still need to check the constraint which takes O and time. But I think you already check those points are taken from the constraint. Why do you need to check it again?
Yeah, okay. So I just took 2 of them.